Welcome back, students. So today we will now look at another important aspect about dislocation, and particularly which gives rise to various phenomena in materials. For example, strain hardening, strengthening effect, and all these things. These arise because dislocations interact amongst themselves. So we will look at the relation which defines this relation, and we will look at some special cases on how these dislocations interact to give you some idea and feel about the interaction of dislocations from which you can build up. In fact, Taylor hardening can also be deduced from this relation. So let's move on. So interaction between dislocations. And when we are talking about interaction, it can be like you may have one dislocation which has its own stress field. So it has its own stress field, and because of it, it may be causing some effect on another dislocation. So it may be causing forces in this direction or also in the z direction. So this will become fx, fy, or fz. And when I say f, remember that it is per unit length. So although I will not explicitly write it as per unit length, but we have to understand that for dislocation, which is, you can say, not of any finite length, or at least we are not considering any finite length, it can have any amount of length. Basically, what I mean to say is that it is not any given length from the beginning of the problem. So it can have a finite length, but not any known quantity. So we will always calculate forces per unit length. So it could be so this is what we can term as dislocation interaction, effect of one dislocation onto this. And for our purpose, that is in our written work, in our theories, what we will do is we will always treat this as dislocation 1. This one will be treated as dislocation 1. This is because when we use the notation 1 and 2, so that you are clear on which particular dislocation we are talking about. So this will be treated as 1, meaning the 1 is the dislocation 1 would be the one due to which effect is being created onto another dislocation, which will be treated as dislocation 2. So it need not be just one dislocation. It could be bunch of dislocations which are together at some distance, and together they have probably some stress field which is causing forces on this dislocation. So again, there will be fx, fy, and fz, and again in this context, this would be treated as 1. So overall, this effect, this bunch would be called f1, and this dislocation. So if we are defining Berger vector and line vectors, then we will call the Berger vector and line vector for this one as 2, and overall whatever quantities we define for this one would be defined as 1. And this overall treatment can also help us understand how much, for example, if this is a dislocation forest or some configuration of dislocation and you want this dislocation to move, then you know this overall formalism would help us understand how much force it needs to overcome, how much external force is needed to overcome this internal forces. internal resistance. So this formalism would also help us understand how much external force is needed for dislocation 2 to overcome internal resistance. In this context, we have the relation which is called as Peach-Koehler relation. So here it is given force, again, do you remember this is per unit length. Sigma, it is the stress field being generated. So here this sigma for this case, it would be generated by one dislocation 1, or in this case, it can be stress being generated because of bunch of dislocation. So you may be able to calculate the overall stress because of this bunch of dislocation, and based on that you would find out what will be the force acting on this. And the B and a line vector that is given is for dislocation 2. So we are calculating the force on dislocation 2, whose Berger vector and line vector are given here. And now I will say that explicitly mention what is F. F is the force per unit length. At any point on dislocation 2. Sigma is the stress experienced by dislocation 2. But it may be generated by this bunch of dislocation, or it may be generated by dislocation 1. But it is being experienced by dislocation 2. And Berger vector B is the Berger's vector for dislocation 2. And line vector is E, is the line for dislocation 2. So you can see that based on this, what we get, if we put in the sigma in the tensor form, so it has 9 quantities. B is a vector, so it is bx, by, bz, and line vector is again a vector, so epsilon x, eta, E, I don't know, it is not eta, sigma dot B cross E. So let's call it E. So it is Ex, Ey, Ez, and sigma has the 9 quantities. And this is how it will be written when you want to calculate the forces acting per unit length on dislocation 2. When the dislocation density increases in the material, then this stress increases. And in turn, the force acting on the dislocation 2 would increase. So this is, you can say, the origin of strengthening when you have higher dislocation density. And if one needs to deform the material, one needs to apply external stress, and that must overcome these internal stresses. So it also means that if you want to deform a material further and further as its dislocation density increases, you need to apply higher and higher stresses, which is also called as strain hardening. Hence, a larger stress is required to cause similar strain when dislocation density has increased. So this is something we can qualitatively see right now, and we would be also able to establish this quantitatively in few minutes. So when you have sigma dot B, then we can basically, this becomes so it is a dot product, so we can as well write it as I sigma j sigma ij into BK. And this is for the sigma dot B part. And when you put it together, you would see this will come out like this, which is, if I write it, what I will do is also write it in terms of XYZ and also write it in terms of 1, 2, 3, because at many places it will be easier to handle this quantity in terms of 1, 2, 3. So it will be sigma 1, 1, B1, sigma 1, 2, B2, sigma 1, 3, B3, sigma 2, 1, B1, sigma 2, 2, B2, sigma 2, 3, B3, sigma 3, 1, B1, sigma 3, 2, B2, sigma 3, 3, B3. So this is sigma dot B, and in terms of 1, 2, 3, and this is sigma dot B in terms of X, Y, Z, and then we take a cross product of with line vector Ex, Ey, Ez are the vectors, and this is the overall form in terms of X, Y, Z, and again I will write it also in terms of 1, 2, 3. Sigma 2, 1, B1 plus sigma 2, 2, B2 plus sigma 2, 3, B3. Sigma 3, 1, B1 plus sigma 3, 2, B2 plus sigma 3, 3, B3. Sigma 1, 1, B1 plus sigma 1, 2, B2 plus sigma 1, 3, B3. And this is 3, 1, 2, and then there is second term over here. So you see this is a vector. Keep in mind this is not no more a determinant or a tensor quantity. It has only 3 values because force field is a vector fx, fy, fz. And over here we have sigma 3, 1, B1 plus sigma 3, 2, B2 sigma 1, 1, B1 plus sigma 1, 2, B2 plus sigma 1, 3, B3 and 3. And this last one is sigma 2, 1, B1 plus sigma 2, 2, B2 plus sigma 2, 3, B3. So this is the overall quantity. And like I mentioned, now we can look at this equation in 2 different forms. So this is XYZ and this is in 1, 2, 3. So 1, 2, 3 basically represents XYZ respectively. But at many places, this one will become much easier or to look at, and also in terms of writing. So both of them are one and the same quantity, and it will give you the value of forces acting on dislocation 2 because of stress field which may be generated because of, this is the stress field quantities which may be generated because of a single dislocation or a group of dislocation or maybe even external forces. So whatever be the source of this sigma, this is affecting the dislocation 2 whose Berger vector are given by B1, B2, B3 and E1, E2, E3 or Bx, By, Bz and Ex, Ey, Ez are the line vectors. So to be able to appreciate this better, what we will do is we will go through some case studies. So let's look at case study number 1. What is this case study? Here we are looking at interaction between 2 positive edge dislocations. So what do we mean by this? So let's say we have dislocation 1 here, another dislocation over here. So if we have, so this is 1 and dislocation. So let's say this is affecting the dislocation 2. So this is 1 and here we have epsilon and I will write as 1 over here on the superscript 1 equal to 0, 0, 1, and the line vector, again I will put superscript 1, which has to be perpendicular to this, so it could be anywhere on this too, but to make things simple we will take it as 1, 0, 0, and this is dislocation 2, so this one is also parallel, so epsilon E2 is equal to 0, 0, 1, and again to make things keep things simple, we will keep the Berger vector 1, 0, 0. So what we are saying is B2x is equal to 1, B1x is equal to 1, and B1y, B1z are 0. Similarly here, E1z is equal to 1, and E1x is equal to E1y is equal to 0. Similarly, E2x is equal to 0, E2y is equal to 0, E2z is equal to 1. So that we have to keep in mind when we are solving this. Now we'll put this. So we know that in this equation, what we get in terms of Berger vector is for dislocation 2. So the only two quantities which are non-zero are Ez and Bx. So only those quantities will remain, and that would mean that this would be here, this would be here, but this is 0, so the whole quantity goes to 0, this whole quantity goes to 0, this whole quantity goes to 0, and this whole goes to 0. And even in this, only Bx is non-zero, By is 0, Bz is 0. Here also Bx is there, By is non-zero, Bz is non-zero. So what we get is F is equal to sigma Yx dx, and to be sure I will now put the superscript 2, and the second quantity is minus sigma x, and then again, and sorry, there is also this E component which is Ez, which is also for 2, and here similarly sigma xx and Bx, which is again superscript 2. So keep in mind this is not square, this is superscript 2 to define that, to inform us that this is for dislocation 2, and this is Ez again 2, and the third one there is nothing left, so it is 0. Now this is Fx, this is Fy, this is Fz, and also per unit length. Okay, I'm not explicitly mentioning it again and again, but that you have to keep in mind. So if that is so, then this is equal to Fx, this is Fy, and this is Fz. So this is glide force acting on it, because if this is the force acting in the x direction, whichever direction, positive or negative, this is called the glide force. So this is glide force acting here. Fy is acting in this direction, which we can call climb force acting on this, but we will not consider at this time about the, or not very much about the climb force, because one, that climb force will also be dependent on temperature. So it is not only this force that has to be taken into account, but also the temperature, and moreover in room temperature deformation, this would anyways be of non-significant unless we are applying temperature also, or unless we are applying doing that deformation at high temperature. Okay, so with that, what we see is that we have this quantity glide, which is sigma Yx, and just for the sake of completion, we will look at the whole equation, how it looks like. So which is sigma xx, and therefore Fx is equal to, now sigma Yx. Sigma Yx, we will remember, is equal to G, and since it is Berger vector has only one quantity, which is x, but this time this x is for first dislocation. So it is superscript 1, and it is x square minus y square, and into this B2, which is, and epsilon z, Ez, but we know that it is equal to 1. So we will just multiply it 1, and on the denominator we have 2 pi 1 minus nu x square plus y square whole square, and Fy again is sigma xx, but with a minus sign, so it is G B x again superscript, then we have y, then 3x square plus y square and there is 2 pi 1 minus nu x square plus y square whole square, and also this is a negative quantity in itself, so overall it will become a positive quantity, and it has again bx superscript 2 into 1, and yes, something I'm missing here, and it has to be x. There's a factor x here. So this is the glide force. This is the climb force acting on the dislocation. Now we will concentrate on this particular equation, which is for the glide, because this one will give us a lot more information about interaction between dislocations. So we are looking at the interaction between two positive edge dislocation, and we know that these are the two forces, and now we have said that climb is something that we can we are not really interested in because it is a high temperature phenomena. Now bringing this equation over here, and assuming that both the Berger vectors are equal in magnitude, so if we have the two Berger vectors in the same with the same sign, then Fx will be equal to GB square x square minus y square by 2 pi 1 minus nu x square plus y square whole square, when both dislocations have same sign. And if both the dislocations happen to be of opposite sign, then we know that this will be, and there will be a negative, sorry, here it is, it will be, one will be negative, and therefore the Fx will be equal to minus GB square x square minus y square by 2 pi 1 minus nu x square plus y square whole square, when both dislocations are of opposite sign. Now here, if we assume that the two dislocations are on the same plane, which means y is equal to 0. So now let's go to the condition where, okay, when dislocations on same glide plane, meaning y is equal to 0. So if you put y equal to 0 in all this, what we get is Fx is equal to GB square and this one will become x cube, and this will be x4. So this will get cancelled, and there will be only x remaining in the denominator. So it will become 2 pi 1 minus nu into x, or I can write it like this, which will have plus when dislocations are of same sign, minus when dislocations of opposite sign. So what is the meaning or significance of having a plus and a minus? So plus implies that the dislocations would try to move in opposite direction, and minus implies that the dislocations would try to move in towards each other. So it would look something like this. So if the dislocations are like this, then the forces acting on them would be like this, repel. So now you can see I have drawn it on the same plane. And if the dislocations happen to be of opposite sign, so this is how it would look like. In this case, the dislocations would attract each other. So dislocations of same sign will repel, and that of opposite sign will attract. This is the main message that we get from this relation. But then we could have also obtained this relation in a slightly different way. Let's look at it in a more, without going through these equations, but then there will be some meaning for these equations, which I will show you again after this. So interaction, the attraction and repulsion can also be predicted on the basis of energy. So when two dislocations of same sign are sitting next to each other, so let's first consider the case of when two dislocations of same sign are sitting next to each other. What is the implication? The implication is the equivalent Berger vector would become 2b, because those two are sitting very close to each other. So it is as good as saying that the two dislocations are. So this will have equivalent Berger's vector of 2b. And therefore, the energy for this new dislocation would be of the order of g into 2b whole square, which would be of the order of 4 GB square. However, if the two dislocations were very far apart, very independent of each other, then their energy would have been GB square and GB square, meaning total energy would have been 2 GB square. So this is energy 4 GB square is certainly greater than 2 GB square when independent. And certainly as any system does not like the energy to increase, therefore the dislocations will tend to stay away. Now let's move on to another case when the opposite extreme, when the two dislocations of opposite signs are sitting next to each other. So in this case, what will happen now that the two Burgers vector, the two dislocations are sitting like this. So this has B and this is minus B, which means the total is equal to 0, 0B. So equivalent Burger vector is now equal to 0. Which means that the energy is of the order of G into 0 square, which is equal to 0, is less than 2 GB square when the dislocations were independent. So what is the message here? That the dislocations will attract each other. So dislocations with opposite B will attract and annihilate, while dislocations with same or similar sign will repel each other. That is the message that we get when we look at this consideration of dislocations being on the basis of the dislocation energy. So this is also the message that we obtained earlier when we were looking at the force. So it's not that the force relation is useless or meaningless. We will look at still another example of force. So now we will again bring our equation Fx equal to GB square and look at more analysis. When dislocations not on same glide plane, meaning y is not equal to 0. Okay, so earlier case was the simpler case where we said that y is equal to 0. But now let's say y is not equal to 0, then what happens? So we will go back to our equation, which says that Fx is equal to GB square x and plus or minus would depend on whether we have the same sign or the opposite sign, which we will look at in a moment. 2 pi 1 minus nu x square plus y square. Whole square. Now, so y is not equal to 0, and let's try to plot the relation okay, so I have drawn a xy plot because what I want to do is I want to plot on the x-axis distance, but I want to plot a distance in a way which will take into account both x and y. So what I will do is let's keep y fixed and I will write x in terms of y. And on the y-axis, I will have force, specifically Fx. So this is Fx, which will be drawn in the, which we can say this is a constant GB1, GB and B2 by 2 pi 1 minus nu y. Now, let's say we have the x as equal to 1y or 2y or 3y or 4y, or in the negative side we have minus 1y, minus 2y, minus 3y, minus 4y. In what it means is that we have a configuration which looks like this. So this is the first dislocation, and the second dislocation we keep the y fixed. So the dislocation, second dislocation can be here, it can be here, it can be here. And this particular location would be of very big interest to us. So let me draw this. So this is 45 degrees. Now what happens at 45 degrees? If you, which means at x equal to y. So when you put x equal to y, we see that fx become equal to 0. And we are, for now, we are considering positive dislocations or dislocations with same sign. Therefore, we are only interested in, or only the plus sign of the force comes into picture. So when we have x equal to y, then force becomes 0. So let's say this is the point. And when x is equal to 0, then also what we would see that this is, there is a factor x here. Therefore, this whole thing goes to 0. So at these 2 points, we know that the forces are 0. What happens in between? Now, let's say at you are little less than x equal to y, meaning you are left of this position. So what will happen? So x is less than 1y. Therefore, this quantity is x square, this is y square. This whole thing is still positive, and this whole thing is positive, but then x square minus y square is a negative quantity. Therefore, this whole thing becomes negative. So the force is acting in another direction, which means that the force is acting in this direction to the dislocation as soon as it moves away from the 45-degree position, and the force is going somewhere over here. So assuming that there will be a minima somewhere over here because it has to come back to this, so the force plot would look like this. And if you go to the negative side, you would see a similar symmetric one where it will have a positive maxima, and the dislocation would want to move in that direction. And if you keep plotting and taking the various values, what you would see is that this will get a relation like this. What do we obtain from this? What does this plot tell us? This plot tells us that when you have a dislocation over here, then it is some sort of equilibrium. But as soon as you move a little bit less left to the left, then this whole quantity becomes negative and the force starts to act in the negative direction. As soon as you make x greater than y, therefore everything becomes positive and the force acts in the opposite direction, and therefore a positive force will act. Now let's come to the position where x is equal to 0, which is right over here. So again, let me draw this. So at this position, it is equal to 0. Now, as soon as you move a little to the right, so you have a little x positive, but it is still less than y, actually much less than y. Therefore, the force is still negative. So if you move a little bit to the over here, then it still has force acting in this direction. And if you move a little bit to the left, then it still has forces acting to the right. which means that the forces are trying to keep the dislocation aligned along this line, 0 degree line. And it is for this reason that we see low angle grain boundaries with dislocations aligned like this. So the dislocations have the tendency, because of the interaction between the dislocations, they are being pulled back to this location. But once a dislocation moves out at from 45 degree position, then it will get thrown off. Then it will not be considered anymore in the array. It will get pushed off. So there is a V-shaped region within which is equal to 45 degree and 45 degree, 90 degree region within which the second dislocation lies. Then it has a force acting on it which tries to bring it back to the alignment, exactly in the line. And once it goes outside that V region, then it is pushed off. Then you are no more my friend, you can go away. It is like that kind of state condition between the two dislocations. And when you have more and more, it gets aligned and forms an array like this. So this is what happens when you have all positive dislocations. But then what will happen if I have two negative dislocations, paired of dislocations with opposite sign? Let's see, it will be very interesting. And what I will do is I will again plot this separately. I don't want this to get messy. And this time I will draw the dislocations in a different color. So again, y distance is fixed. And this is the distance x, and at some angle which is equal to 45, which is of interest. And here, if you plot the graph, you would see, okay, first let me put 1y, 2y, 3y, 4y, and over here minus 1y, minus 2y, minus 3y, minus 4y. Now if I put it like this, then and use the equation here again, but this time the dislocations are of opposite sign, so the negative one will be in picture. And from this relation, or from this, you can see it will be symmetric of this, just inverted symmetry. So the plot we will get would look something like this. So it will be 0 here, it will be 0 here, it will be 0 here. Only it will have maxima over here, and it will have a minima over here. And if you plot it further, you will have something like this, and you will have something like this. Now let's look at what is the meaning of this. So what it means is that if you are at 45 degrees, then of course it is equilibrium, although we'll show it is in the previous case we saw it was an unstable equilibrium. Now if the dislocation moves a little bit to the left, say left somewhere over here, what will happen? There is a positive force acting on it. Positive meaning in this direction. So the forces are trying to bring it to this position. And if the dislocation moves away from 1y, or x is greater than 1y, then it is over here, and the forces are acting in this direction, meaning now they are trying to bring the dislocation into equilibrium in this position. So this 45-degree line becomes the stable equilibrium position. Earlier this was an unstable equilibrium position. In this particular case where we had positive dislocations, then dislocation would try to move away from this in this direction or in that direction, and the stable equilibrium was over here. But now we have a stable equilibrium over here, and if you look closely, what you would see is that there is a unstable equilibrium over here. From this plot, you can see that if the dislocation moves a little to the positive x, then it has forces acting in the positive direction. And if it moves a little to the left, it has forces acting in the negative direction. And there will also be a equilibrium, stable equilibrium position over here at minus 45 degrees. So this is a stable equilibrium. This is a stable equilibrium, meaning the forces want to bring the dislocation back to this position, while this one is a unstable equilibrium. And now that we are talking in terms of stable equilibrium and unstable equilibrium, let me also mention here that this one is stable equilibrium. And this one, and there will also be some here at minus 45 degree. These are unstable equilibrium. This equation, which is telling us the force acting on the dislocation, can also be used to derive the Taylor-Harding relation. But for now, here what it is showing us the forces required for forces acting on this dislocation, or in other words, how much force would be required for this dislocation to move in the presence of another dislocation. So what we realize is that a positive dislocation would form an array like this, and a negative dislocation would also form an array, but at 45 degrees. So this one, if you look at it, would form a array something like this. So this is just part of it, but next line would again be all positive at 45 degrees and so on. So this is the condition we have looked at where dislocations, two positive edge dislocations are interacting. Next, we will move on to another case study where two screw dislocations are acting. So for the two screw dislocations, again, we need to define what are the line vectors. So for dislocation one and dislocation two, we know that here I will put it as a superscript is equal to 0, 0, 1, and Berger vector for this one is equal to, because it is a screw dislocation, it has to be same as the line dislocation. And again, we are taking a case of two parallel screw dislocations. Okay, so parallel screw dislocation, and therefore E2 superscript 2 is equal to 0, 0, 1, and Berger vector superscript 2 is equal to 0, 0, 1. And the force acting on dislocation 2 would be, this is the general relation, so this is what would be the force acting on the dislocation 2. Over here, the Berger vector and the line vector are with respect to dislocation 2, so it has only z component, or basically epsilon 2 z is equal to 1, b superscript z is equal to 1. And since only Ez and Bz are there, so all other quantities would get cancelled out, or basically they turn to 0. Then again, Bz is the only quantity here, all other go to 0, Bx, By, Bx, By, they all go to 0. And what we are left with is F. And remember, this is a vector. So there are 1, 2, 3 quantities here. Sigma YZ, BZ, EZ, and I will put the superscript 2 to distinguish the fact that it is the Berger vector and line vector for dislocation 2. Of course, in our case, it happens to be same in magnitude, but we want to keep things distinguished. And here we will have sigma XZ with a minus sign, and again BZ superscript 2, EZ superscript 2, and line vector 0. So this is the force acting on the dislocation, and like we mentioned earlier, this is Fx, which is the glide force, and Fy, which is the climb force. So again, we are interested only in the glide force, and here the Yz. So if we go back, we will see that G, and there is Berger vector for, and if we take the magnitude, we have to take only the magnitude of since it is only Z, so B superscript 1 Z by 2 pi into cos theta by R, and here into B, which is equal to Z superscript 2, and E we will take as 1. And cos theta we know can be so I will now just write B1, B2, and cos theta can be written as cos theta by R can be written as X by X square plus Y square. So this is the force acting on the glide force acting on the screw dislocation 2. And here also what we see is that when dislocations of same sign, then Fx greater than 0, which means repel. When dislocations of opposite sign, then Fx is less than 0, attract. So this is the relation or the forces acting between two parallel screw dislocation. And here also we see that the same thing turns up. The dislocations of same sign will repel, and dislocations of opposite sign will attract. And again, we could have used the same argument of energy also, and we would have obtained the same relation. So overall, we can say whenever dislocations are of same sign, they will attract, and whenever, they will repel, and whenever dislocations are of opposite sign, they will attract, and they can also annihilate each other. In fact, this is also something that happens very often at higher temperature where recovery is taking place. Dislocations get annihilated. Next, what we will look at is the interaction between a screw dislocation and an edge dislocation where the line direction is same. So this would be very interesting, as you would see. So here we will write So this is dislocation 1, which we will be calling as, so this is our edge and this is screw. And line vector is same. So we will have E1 equal to 0, 0, 1, and the line vector, the directions, they are parallel. Again, I have not mentioned it explicitly, but we are considering the case of parallel dislocations. So epsilon subscript 2 is also equal to 0, 0, 1. And here it is edge dislocation. So Berger vector is equal to 1, 0, 0. And here the dislocation screw dislocation. So the Berger vector will also be as same as the line vector. Okay, so now we have, that this is the force we are basically calculating effect of edge dislocation on screw dislocation. And since we are talking only of two dislocation, it will be the same force that will be acting on from the screw dislocation onto the edge dislocation. So that will not change. Now that we have this relation, we will look at what are the quantities that will go down to 0. So here we have only Ez and here we have only Bz. Every other quantity must go to 0. Therefore, this whole quantity goes to 0, this whole goes to 0, this whole goes to 0, this whole goes to 0. And Bz is the only non-zero element. So Bx, By would also go to 0 over here and over here. And therefore, the force that we obtained earlier is same here or there, but there will be one major difference, as we will note. Sigma Yz Bz, where Bz is for the 2, Ez for the 2, and then we have sigma Xz Bz2 Ez2, and the third quantity is 0. Okay, so it looks like it is all same as the previous one and nothing is new. Okay, then let's try to find out what would be the sigma Yz. Now remember, this sigma Yz is because of edge dislocation. Sigma Xz is because of edge dislocation. But for an edge dislocation, Xz and Yz and Zx and Zy are non-existent quantities, meaning they are 0. Which means that the total force acting is equal to 0. There is no force acting on the screw dislocation because of the edge dislocation, or vice versa. That is, no force is acting on the edge dislocation because of the screw dislocation. So let me, no force or vice versa, meaning no interaction. Now, isn't that very interesting? So why is it that screw dislocation and an edge dislocation, which are parallel to each other, do not interact with each other? Okay, I will leave you with that thought, with that question. So look into that, try to find a reason why there should be no interaction. Only when we are talking about, so I have been, this calculation I've shown is when they are parallel. Need not be true when they are perpendicular to each other or at some other angle. Okay, so keep that in mind. Only when they are parallel to each other, anywhere, it doesn't matter. If they are parallel, then we have shown that there is no interaction, there is no force acting on either of them because of the other one. So why is it so? It is for you to find out. So I will end this lecture over here. Thank you.